Thank you for joining us on Synthesis Workshop. Today is the third in a series of Research Spotlight episodes which have been made possible through a partnership with Team of Chemistry aimed at highlighting some of the great work done by Team of Chemistry Journal awardees. On today's episode, we're joined by Dr. David Leboeuf. David obtained an engineering degree from ESPCI in Paris before pursuing his PhD at UPMC Paris 6. There, he worked with Professor Max Mulacria on reactions catalyzed by cobalt, rhodium, and gold. He subsequently worked as a postdoc in the Frontier Group at the University of Rochester, studying copper-mediated Nazarov reactions, before doing another postdoc at ICIQ in the Echevarren Group focused on gold catalysis. Following these international research experiences, he became a CNRS-appointed assistant professor and later associate professor at ICMMO in Orsay, France. In 2019, he joined the Supramolecular Science and Engineering Institute, ISIS, in the Laboratory of Chemical Catalysis located in Strasbourg. And from there, I'll let you get started, David. Thank you for joining us to share your group's work.
First, I would like to thank Matthew and Team Fairlight for this kind invitation. It is a great pleasure to be here to present our recent results at Synthesis Workshop. Today, I would like to talk to you about the development of new and simple strategies to access original nitrogen-containing scaffolds. We believe that this type of research is critical to open new horizons in drug discovery, as our bias tends to restrict our research to non-natural products and biologically active compounds. Over the last years, an important part of our research program has been dedicated to the chemistry of cyclopentinones and how to use them to create molecular complexity from readily available precursors. As you know, cyclopentinones, due to their numerous reactive sites, represent fundamental building blocks for the synthesis of natural products and bioactive molecules. Currently, the Nazarov electrocyclization, the Pausen-Korn reaction, and other related cycloadditions are amongst the main methods to generate such scaffolds from linear precursors. Another less common strategy is the Piancatelli rearrangement, which was discovered in 1976. This transformation is based on the stereoselective rearrangement of two furyl carbinols into trans 4-hydroxycyclopentinones under typically highly acidic reaction conditions. Interestingly, this process is a rare type of reaction that directly transforms an heterocycle into a carbocycle. Regarding the mechanism, it first involves the protonation of the furyl carbinol to generate the corresponding carbocation. One of the resonance forms can undergo a nucleophilic addition of water. After a ring opening, the reaction proceeds through a 4-pi convertatory electrocyclization to provide the target 4-hydroxycyclopentinone with an exclusive trans stereoselectivity. This reaction was quite popular in the 80s and 90s because it enables a straightforward access to prostaglandin derivatives. However, at first, the reaction conditions were quite harsh, limiting its functional group tolerance. As a result, method development using this reaction stopped until about 10 years ago when milder catalytic systems, featuring Lewis acid catalyst, appeared. For our part, we wanted to develop a nitrogen version of this reaction, a NASA-Piancatelli cyclization, to synthesize 4-aminocyclopentinones. Indeed, these compounds can be extremely valuable because they can serve as direct precursors to access aminocyclopentitols, whose scaffold is present in a large variety of bioactive molecules, such as peramivir, that is used for the treatment of influenza, triazoline, which is an inhibitor of glycosidase, or pactamycin and agelastatin A, that have anti-cancer properties. Following the pioneering work of Reid Dealanis group with the utilization of dysprosium salts, we succeeded to develop milder reaction conditions by using a calcium catalyst in the presence of an ammonium salt in hexafluoroisopropanol as a solvent. Here, the role of HF-IP is critical, as its inherent properties, strong hydrogen bond donating ability, low nucleophilicity, mild acidity, and a relatively high dielectric constant, favor the activation of the substrate and the stabilization of the reactive cationic intermediates. To cite but a few limitations, the reaction was not compatible with more basic alkylamines, which are prone to sequester the catalyst, and with carbon-5 substituted furyl carbinols because of the steric hindrance generated during the addition of the nucleophile. From there, the idea was to use the Piancatelli cyclization as a cornerstone to build more complex molecules by combining this reaction with a second transformation. One class of substrates that drew our attention was tetrahedrobenzoazepines, which represent an important class of medium-sized nitrogen heterocycles whose framework can be found in a large range of bioactive molecules, including tolvaptan, benazepril, and evacetrapib. As a result, over the last years, several simple and efficient methods to access tetrahedrobenzoazepines have started to emerge. On the other hand, bridged tetrahedrobenzoazepines remains an elusive subclass of this family, the development of which has been clearly underexplored. The limited output for these challenging molecules might find its origin in the difficulty to prepare them, which has hampered any real study on their potential bioactive properties. For instance, at that time, only a single method to prepare such compounds had been reported in the literature by the group of Porco, via a 3+2 photocycloaddition. In this context, we wonder whether the Piancatelli cyclization could be exploited to close this gap. Thus, by taking a close look at the compounds generated during the cyclization, we reason that the introduction of a nitrogen functionality on the carbonyl moiety might be the answer to this challenge. In practice, once the Piancatelli cyclization is complete, the addition of a base to the reaction mixture will trigger a Michael addition and grant access to bridged tetrahedrobenzoazepines in a one-pot sequence. Since the cyclization ends up installing the substituents in a trans relationship, it should prevent any steric hindrance issue during the second step. Conceptually, this route would also yield the target compounds with two additional synthetic handles, a ketone and an amine, which could be used for diversity-oriented synthesis. In our initial investigations, we explored the reactivity of a 2-furyl carbinol bearing a sulfonamide moiety with 4 iodoanilines as a nucleophile. Using the same type of promoter system previously mentioned, and the triethylamine as a base for the second step, the target bridge tetrahedrobenzoazepine was obtained in 91% yield. The reaction was also scalable without any setback in terms of yields. With these optimized conditions in hand, we assessed the scope of the reaction. The tosyl group can be replaced by an orthonosyl one, whose cleavage occurred smoothly to afford the unprotected amine in 89% yield, upon treatment with thiophenol and potassium carbonate. The reaction was not limited to anilines, but could be also applied to hydroxylamines. In addition, the transformation was compatible with tertiary furyl carbinols and the presence of a naphthyl moiety. Another interesting feature is that phenol could be also employed in this type of reaction sequence to provide the corresponding bridge tetrahedrobenzoxepines. Lastly, we demonstrated that N-alkyl sulfonamides could be used instead of benzene sulfonamides. However, the diastereoselectivity of the reaction sequence proved to be moderate. One synthetic limitation is that the reaction required the presence of an electron withdrawing group on the nitrogen functionality to soften its nucleophilicity and prevent any side reaction. Using the same approach, we then turn our attention to piperazinones, whose synthesis has been well described, as they can be used as direct precursor to piperazines, which are key players in drug discovery. Yet, among piperazine derivatives, the synthesis of cyclopentapiperazinons remains clearly underdeveloped, even if this scaffold is featured in agelastine A, which possesses a broad range of potent biological properties. Surprisingly, no general method for the synthesis of such skeletons had been reported. In this context, we thought about addressing this anomaly and open a new route for the straightforward construction of those derivatives. To achieve this objective, we envision that combining the Piancatelli cyclization with the use of alpha-LOamides will allow us to rapidly forge cyclopentapiperazinons in a one-pot fashion following a formal 3+3 cycloaddition. Alpha-LOamides are indeed common precursors to azaoxyallyl cations that can be easily generated in situ in the presence of a base. Azaoxyallyl cations can be viewed as zwitterionic 1,3 dipoles, even if their structures are in fact closer to an aziridinone or an oxyran to imine. Since the seminal work of Jeffrey's group, the use of azaoxyallyl cation intermediates has been extensively studied in synthesis to provide a large variety of nitrogen-containing heterocycles, as exemplified by Wu. What is interesting is that fluorinated alcohols, thanks to their hydrogen bond donating ability and their capacity to stabilize cationic species, are the solvents of choice to study the reactivity of azaoxyallyl cations, which supported our strategy. We were pleased to see that the reaction sequence envisaged worked smoothly to yield the target cyclopentapiperidinone in 82% yield. Regarding these compounds, we wanted to demonstrate that we could selectively cleave the functional groups on the nitrogen depending on the reaction conditions employed. In the presence of a molybdenum complex, the benzyl oxide group could be selectively removed in 74% yield. On the other hand, the cleavage of the paramethoxyphenyl group proved to be more problematic. The deprotection in the presence of cerium ammonium nitrate occurred without any problem, which was confirmed by NMR. The resulting product unfortunately rapidly decomposed. To show a few examples, we study for instance a furyl carbinol incorporating an azide moiety. This reaction sequence furnished the corresponding product in 81% yield, with a remarkable control of the diastereoselectivity on 4 contiguous stereocenters. The relative configuration of the functional group was ascertained by noisy analysis. Via this method, it is possible to install all the nitrogen functionalities present in pactamycin with the right arrangement, without forgetting the oxygen and the methyl groups as well. In the case of a substrate bearing a phenyl group at the carbon-3 position of the furan, the diastereoselective reduction of the ketone generated was achieved to give the corresponding aminocyclopentytol with a nearly complete control on 5 contiguous stereocenters. For the last part of this presentation, I will switch to a different type of reactivity, namely formal high-order cycloadditions. In the last decade, azaoxyallyl cations are not the only cycloaddition partner to have made a breakthrough. We can also cite tropons, which are non-benzenoid aromatic 7-member rings. They have also recently emerged as fascinating partners for cycloadditions, notably for high-order cycloaddition, such as 6+6, 8+2, or 8+3 cycloaddition, which remained clearly underexplored in synthesis. In this context, our idea was to combine these two motifs to access unprecedented 7,6 fused nitrogen-containing heterocycles through a formal 8+3 annulation in a metal-free transformation. When we started this work, there was only one related example by the group of Guo using aziridines as cycloaddition partners. During our optimization studies, we found out that using triethylamine as a base yielded the target products in overall good yields. Both isomers could be separated by flash column chromatography. Replacing the benzyl substitution by an allyl or phenyl group did not affect the transformation. However, depending on the substitution pattern, we can obtain either one isomer or the other one, which we didn't succeed to fully rationalize. The transformation was also compatible with secondary bromides to generate the corresponding diastereoisomers whose configurations were probed by noisy analysis. During our investigations, we also evaluated the reactivity of an alpha-haloamide bearing chlorine substituents, which gave exclusively a spiral compound in 48% yields without any further transformation. We hypothesized that the electron withdrawing nature of the substituents precluded any 1-2 shift, and thus the reaction was shut down at the first step. Finally, the reaction is not limited to the simple tropon, but could be also applied to 2-phenyltropon. Regarding the mechanism, an important example was the case of a cyclohexyl tether, as the reaction occurred at a slower rate, delivering a spiral compound as a major product. By increasing the reaction time, we succeeded to observe the nearly complete conversion of this spiral compound into the expected products, with however a moderate selectivity. To rationalize the mechanism, DFT computations were carried out on our model reaction. As anticipated, the azaoxyallyl intermediate converge as a 3-member ring which reacts with tropon to generate a zwitterionic species. Attack of the negatively charged nitrogen atom to the oxonium center leads to a spiral intermediate, which was observed experimentally. However, from there, we failed to model a pathway to the products observed. A serious lead was obtained after protonating the spirointermediate that opens to form the corresponding tropylium. It was not possible to form a 6-member ring from it, but removal of a proton and optimization led to the major compound in the stepwise fashion after deprotonation. This raises the question of the proton source, the most obvious one being HF-IP. Regarding the minor product, it could be obtained following a 1,7 hydride shift. To summarize, the reactions that I've presented today only represent a small sample for the complex cascade reactions that we developed to access original densely functionalized nitrogen-containing heterocycles. Currently, we are trying to engage into collaborations to study the biological activity of those molecules. To this end, it is important to stress that all those reactions were scalable. To finish, I would like to thank all the collaborators and students who were involved in those projects, especially Shendong, Guillaume, Boubacar, Lucille, and Bastien. They all did an amazing work to give life to these ideas. I would like also to thank Professor Vincent Grandon, who carried out all the mechanistic studies by DFT computations, and the French National Research Agency that was one of the main funders for these projects. Lastly, I would like to thank Matthew for hosting this episode.
Thank you for tuning in for this Research Spotlight episode, and thank you to David for a great talk. Thank you as well to Team of Chemistry for making this episode possible. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.